Let's take a look at the homework on page 126. And the concept for this homework is focusing primarily on differentiability. However, I gave you some other instructions to also consider continuity to give you opportunity to practice your justifications of continuity as well as limits to practice your justifications there. So let's begin by taking a look at number 81, and we are looking for the values of x where the function is not differentiable. Now remember the things that we're looking for a function to be not differentiable. We're looking easily at a discontinuity. A function is not or has no derivative or instant rate of change at a discontinuity. So if we see one of those, that's a quick, easy identify. The second thing that we are looking for, now remember this is for our brain, we are looking for a sharp turn, but that's just for our brain to remember. The justification and how we justify that, we're not going to say that a function has no derivative because there's a sharp turn. That's just a look for. And the third thing, and okay, here's your clue. We're looking for these things, but these are not our justifications. The third thing that we are looking for is a cusp or a dimple, and a cusp, remember, looks something like that. So if we see those three things, we know that there's a place where there's no instant rate of change or no derivative. All right, so coming back over here to the graph in number 81, clearly I can see a vertical asymptote at x equal to -1. So there is a discontinuity there. This is all the stuff that's going on in my brain. So I know that the function will have no derivative at x equal to -1, but there is a derivative everywhere else on the graph. Because if you think about it, you could draw tangent lines here's just an example, everywhere else, that's not a good tangent line, on the graph. So if you take a look at my answer that I've typed up for you, the first thing I say is that f of x is not differentiable at x equal to -1 because f of x is not continuous at x equal to -1. And that's all you need to say when you are justifying the differentiable piece of the function. Now my directions went further and said, okay, after you do that, look at that particular value of x that you just identified and talk about the continuity. So we've already said that x, in this case, x is not continuous at x equal to -1. And remember our reasons there for continuity. I'll write them over on the other side. The first one is f of c is not defined. In other words, there is no y value. The second reason that a discontinuity might occur is that the limit as x approaches c of f of x does not exist. And then the third reason is a combination of the two. Maybe there is a y value, maybe there is a limit, but the limit, let's see if I can squeeze it in here, as x approaches c of f of x does not equal f of c. In other words, the limit does not equal the y value. In this case, we've already stated that there's a vertical asymptote, but that's not my reasoning, which means that there is no y value. So f of x is not continuous at x equal to -1 because f of 1 is not defined. There's no y value. That should be -1 actually. F of -1 does not generate a y value. And then thirdly, I asked you to look at whether or not there's a limit at this particular value of x, or if the limit exists. So in this case, the limit from the left and the right do not agree with each other. We already know that we have a vertical asymptote, so the limit does not exist because in this case, I said the limit from the left and the limit from the right do not equal each other. You could also get away in this case with saying because of unbounded behavior. The reason that I said the left and right limits, even though we are going in this case from the left towards, let's change colors here, from the left towards -infinity and from the right we're traveling towards positive infinity, that's where I thought it was more appropriate to say that the left and right limits do not agree. But unbounded behavior would also work here. All right, let's clear away that and let's go to number 82. In number 82, they've already provided the graph for us. And this one can be a bit tricky. I see a sharp turn, not a cusp. Remember, a cusp is when we dimple from the left and we dimple from the right, and from both sides we seem to be approaching the same, the slopes seem to be moving towards one another. And in this case, they're moving towards being vertical. But here, if you look at the way this graph, it's a reflected parabola. And if you were to think of the tangent lines following this curve right here, and the tangent lines following this curve right here, they are not moving towards undefined. So this is that case that's very similar to like the absolute value that we looked at. And in fact, you do see the absolute value right here. So first we're going to say that this function is not differentiable. In other words, there's no derivative, no instant rate of change at x equal to -3. And that is because the derivative, not the limit, the derivative from the left side does not equal the derivative from the right side. Now, how am I saying that? Look very carefully because you're going to have to be able to do that yourself. So right here, I'm talking about this expression right here is the left derivative, not the left limit. It's a derivative statement that uses a limit. So here is y number 2, which is the function. There's f of x. The y value when x is equal to -3 is 0, so that's y number 1 over x number 2 minus x number 1. So your slope formula is right there, and we're saying that the derivative from the left-hand side is not agreeing with the derivative from the right-hand side. Those tangent lines would be moving you towards two different values. Same thing happening at x equal to, if you come back over here, at x equal, where's my pen? At x equal to 3. So the function given is not differentiable at x equal to 3 for the same reason. The left derivative does not equal to the right derivative. Very important that you practice writing that statement out and how to write it and what it looks like. Be very familiar with that. The next thing is continuity. In number 82, the function is continuous at x equal to -3 and is continuous at x equal to 3, so we don't have a statement there. And the limit exists at x equal to -3 and x equal to 3, so we don't have to make a statement there. All right, moving on to number 83. 83 is your classic cusp. In other words, from both sides, we are approaching that vertical tangent. So if we remember that we called it the bird function, the bird will flap its wings all the way to a vertical tangent if we were to zoom in on that local linearity. And I encourage you, you can take your calculators, particularly on number 82, if you want to see or show that in number 82, the graph does not become locally linear at -3 and 3, you can do that zooming in like we did in class. And in number 83, if you zoom in on that, you will see that the graph does go locally linear, but it becomes a vertical line, and the slope of a vertical line is undefined. So in number 83, I'm going to say that the function f of x is not differentiable at x equal to 3 because there is a vertical tangent at x equal to 3. The function is continuous at x equal to 3, and the limit does exist, so I don't need to justify that. 84 is like the first one, number 81, except for this time there are two vertical tangents. So at x equal to -2, not vertical tangents, vertical asymptotes, I'm sorry. In number 84, there are two vertical asymptotes. So there are two discontinuities. So the function has no derivative at x equal to -2 because f of x is not continuous. Same thing at x equal to +2, the function is not continuous. And then the reason the function is not continuous, separate idea, well, not separate, but we're doing our separate justification. The function is not continuous at x equal to -2 because there's no y value at -2. Notice how I wrote it. I didn't write no y value. I wrote f of 2 is not defined. I must write mathematically. And the same thing at f of x equal to 2 because there's no y value. There's another vertical asymptote there. And then when I justified the limits, I said in both cases, the left and right limits do not agree because we're approaching two different infinities, so take a look at that. But again, you could get away with unbounded behavior for that justification. All right, number 85. Notice in number 85, when we're trying to find if there is a derivative, one thing you could look at, there's only a one-sided limit here. So as we approach 1 from the right-hand side, you can see it's like half a dimple. And so it looks like we're approaching vertical from the right-hand side, but we can't approach from the left-hand side. So for a number of reasons, in number 85, the graph is not differentiable at x equal to 1 because, I mean, you could say the limit as x approaches 1 from the left side. In other words, that's not in the domain, does not exist, so you can't even say the left and right limits don't agree. Or you could say, approaching it from the right-hand side, that there would be a vertical tangent there. Finally, number 86, we have a piecewise function, and clearly there's a discontinuity at x equal to 0, so that's going to be why the function has no derivative at x equal to 0. So that's easy, not differentiable because no continuity. The function is not continuous at x equal to 0 because the limit as x approaches 0 of f of x does not exist. Now be careful, I'm not sure what you wrote, but a lot of times students don't notice that there is a y value down here. So f of 0 is -4. The problem is that the limit from the left and right do not agree. Therefore, the function is not continuous because the limit does not exist. And then I also just stated, let's see if I can slide this down for you. I actually can't. Let me do this. The limit does not exist because the left and right limits, written mathematically, don't write the words left and right limits do not agree. All right, so that is your work for page number, whatever it was, 126. Hope it helps.